So now we're going to talk about the different types of solutions, and first we're going to start off with solutions of gases in liquids. So the easiest example to illustrate this type of solution is just like a fizzy soda, so like a Coke or whatever type of soda, carbonated water. And in this solution, we have a gas dissolved in a liquid. Now, for gases dissolved in liquids, they have a certain degree of solubility. This solubility is affected by pressure. So, what determines the fact that those gases are affected by pressure in terms of their solubility is the solute and solvent interactions. So, the simple answer for solute-solvent interactions is like dissolves like, but it doesn't explain necessarily everything. So the stronger the solute and solvent interaction, for gases specifically in liquids, the greater the solubility of the solute in that solvent. So the more that these solutes and solvents like to interact, the more IMFs they have, then it makes sense that they would want to dissolve more, so the solubility is larger. So to demonstrate this, let's look at this table of different gases. Now, what is different about each of these gases, the major difference, is the molar mass. So as we go down this table, we see that krypton is the largest molar mass gas on here. So remember how we talked about LDF? And how LDF, where the larger the molar mass, then the more LDF you have, right? Which also means more IMF overall. So because of this, I want you to take a look at the solubility. So the larger molar mass gas, we also see the largest solubility. And the smallest, we have the smallest solubility. So the more IMFs you have, in this case they're LDF, London dispersion forces, then the greater the solubility. So we can actually calculate this relationship mathematically through something called Henry's law. Henry's law allows us to determine the solubility of a gas, and the overall relationship is that the solubility is proportional to the partial pressure of the gas above the solution. So remember how we learned about how liquids in a closed container have a gas above them, and this gas exhibits a partial pressure. So the partial pressure will directly affect the solubility. So here we have the equation for Henry's law. This C right here is the solubility. This K is a constant. It's a proportionality constant, which I spelled wrong right here. And it depends on the gas, so they're unique to each gas. And then finally, this PG is the partial pressure of the gas. I want you to look at this graph right here and how as pressure increases, so let's say when we go from 0 to 1, right, the pressure is increasing. We also see, so if we take a look at, nitrogen. When we start at 0, the solubility is very low, and then when we increase at 1, we see that the solubility is higher. So the higher the pressure, the greater the solubility that you will have. So in this problem, we are applying Henry's law. So it's supposed to say at 20 degrees C, the concentration of dissolved oxygen in water exposed to gaseous oxygen. So we are looking, let's say we're in a closed container, right, and there's water, and there's oxygen dissolved in here, but it has gaseous oxygen, floating around. So just picture that. So it's exposed to gaseous oxygen at a partial pressure. So this gas above here has a partial pressure of 101.3 kilopascals. And what they also tell us is the amount of oxygen dissolved, right? Mole per liter is basically a concentration. So they're telling us, and I know it doesn't seem so obvious, but they're telling us the solubility. So this was the partial pressure and this is the solubility. 1.38 times 10 to the negative third mole per liter. So overall, these are knowns, right? Use Henry's law to determine the solubility of oxygen when its partial pressure is this. So what we have here is we have, for this first part, we have both this partial pressure and a solubility corresponding to that partial pressure. Because of that, we will be able to calculate and find out what our constant is for oxygen being dissolved. So we're first going to solve for our K. And to do that, let's go ahead and rearrange our equation. So I'm going to divide both sides by PG. That gives me K equals CG, so the solubility over the partial pressure. And then we just plug that in since we already have that. So CG is 1.38 times 10 to the negative third mole per liter. And then we divide this by the partial pressure. And we should get 1.36 times 10 to the negative fifth. And the units, they should be mole per liter times kilopascal. So this is our K. And now that we have our K, we can just go ahead and plug in. So we are searching for a new solubility. We're searching for a solubility at this particular pressure, right? So it'll change depending on the pressure. Remember that graph where as you increase the pressure, the solubility increased? So same thing here. So, but in this case, we're actually decreasing the pressure. So take note of that. But now we just plug and chug. So Cg, our solubility, will equal to our constant. And make sure to write your correct units, liters times kilopascals, times that new pressure, which is 20.7 kilopascal. So kilopascal cancels out and we end up with a new solubility. So I ended up getting 2.819 times 10 to the negative fourth mole per liter. Now, based on sig figs, we should keep it at 3, right? These are showing that our minimum, our lesser amount of sig figs is 3. So it should end up being 2.82 times 10 to the negative fourth mole per liter. Now, does this make sense? So as you increase pressure, your solubility should also increase. If you decrease it, you know, it's the same pattern. So if you decrease pressure, your solubility should also decrease. In our case, we started at 100 with this amount, and now we are at 20, so we decrease. So our solubility should decrease, and it actually does. So I want you to look at the magnitude of this. So this is times 10 to the fourth, while this one was times 10 to the times 10 to the negative fourth. And whereas the first one, the original one, was times 10 to the negative 3, which is bigger. So it makes sense that now it's smaller since we have a lower pressure. So now we're going to talk about solutions of liquids in liquids. So we first are going to start off with some terms that I have probably mentioned already, and you're probably already familiar with, but just repeating them because they apply here. So miscibility. Liquids that mix together are miscible. Liquids that do not mix together are immiscible. So for example, hexane is a solvent. It's nonpolar, while water, on the other hand, is polar. So we consider them immiscible. And you can see how they are immiscible by whenever you add them together. Hexane will float on top. It'll be two different layers because they don't dissolve together. But there can be partial miscibility. So here, for example, we have bromine liquid. Here we have water. When you mix them, you will have some of that that bromine, I literally just said bromine, that bromine dissolve into the water, but not all of it will. So you see that most of it is still, you know, not dissolved into the water, but you can have partial miscibility. So finally, we have solids in liquids, solutions of solids and liquids. Both ionic and covalent solids can dissolve in liquids. Usually they will require heat, so it's an endothermic process. And one thing that we have found, or scientists have found, is that adding heat favors dissolving these solids. Now think about it. Whenever you have hot coffee, it will dissolve sugar a lot easier compared to if I have iced coffee. If I try to add some sugar, it's gonna either not dissolve or take longer. So higher heat, so increase in temperature, increases the solubility of solids. And we can see it here how for most of these, as the temperature is increasing, we also see an increase in solubility. So we've talked about just regular solution making, right? You dissolve a solid into a liquid, it dissolves, and you get a solution. But what about the opposite? The opposite is actually called crystallization. So it's the opposing process of solution making. And you can see it here like as an actual reaction where we start off with the solute and the solvent, we dissolve it, versus the opposite, it's called crystallization. So when the rate of the opposing processes are equal, if you keep adding solute, it will not dissolve. And what you end up getting is a saturated solution. Whenever you have not reached the amount that will result in crystallization, if you reverse the reaction back, then you have an unsaturated solution. So it's not at the complete mark. So for unsaturated solutions, you can think of this meme where the Hulk is talking about how he sees solute. I don't remember what this exact line was, honestly. But yeah, that's there to help you remember. So there are also supersaturated solutions. In these solutions, the solvent holds more solute than is normally possible at the temperature that it's at. And these solutions are actually really unstable. So let's say you add a seed crystal, like they're doing right here. Or if you scratch the side of whatever container it's in, it will disturb the solution and it will cause all of the solute to crystallize out, and you end up having all that solid. So again, to recap what the effects of temperature are. For most solids, as temp increases, solubility increases. It's not always true, but it is generally true, and you can see it how a lot of them do increase in this way. For all gases, temperature increases, but solubility will decrease. So just to give you an idea about this, cold rivers have higher oxygen content than warm rivers. So here we can see that as temperature is increasing, our solubility is decreasing for most of these gases. So to tie together a little bit of what we learned in the previous chapter, for example, with organic molecules in water, polar organic molecules dissolve in water better than non-polar. And it makes sense because if you think of IMFs, for example, hydrogen bonding, if you have the possibility for that of an organic molecule containing a OH bond. So for example, let's say we have methanol, which is CH3OH. That OH right there can hydrogen bond with the water, with the potential contacts of hydrogen bonding in water. So because of that, you have a higher solubility. And when comparing just polar versus non-polar, obviously, you know, the polar is going to dissolve better in water. So to give you another example of how solubility is important, here we have some fat-soluble vitamins like vitamin A versus water-soluble vitamins. So fat-soluble vitamins, they will be readily stored in fatty tissue versus water-soluble vitamins like vitamin C. They can be excreted out of your body pretty easily because, you know, they're dissolved in water, so they can be excreted in urine. Versus fat-soluble vitamins, they can get stuck in your fat tissue. So for example, I remember my biochem professor, he would talk about how his wife was facing like trouble. They were trying to have a child, and they were facing trouble, and he thought it was because of the birth control, which is fatty soluble. He thought it was being like released slowly because she was losing weight. So they were having trouble because of that, and I think it prolonged how much time it took for them to conceive their child. So that's just an example to demonstrate how solubility is important, especially in the body.